In the last lesson, we treated lesson 1. So in this tutorial, we're going to jump right into lesson 2, that is called Zombies Attack Their Victims. So you can see this is lesson 1 that we treated in the last tutorial. This is 100% completed already. So let's jump right into lesson 2. I'll just click the start button, then takes us right into lesson 2. Okay, so it says you've made it to lesson 2. Impressive human, you're a better coder than I thought. Lesson 2 will teach you how to multiply your zombie by feeding on other life forms. So blah blah blah. So let's just go ahead and click the start button right here, and it will take us right to chapter 1 of lesson 2. Okay, so you're welcome, and let's jump right into it. In lesson 1, we created a function that takes a name, uses it to generate a random zombie, and adds that zombie to our app's zombie database on the blockchain, right? Okay, so in lesson 2, we are going to make our app more game-like. We are going to make it multiplayer, and we'll also be adding a more fun way to create zombies instead of just generating them randomly. How will we create new zombies? By having our zombies feed on other life forms. Okay, so in this chapter, we'll be creating a feeding functionality for our zombies. All right, so our zombies will be able to feed on other life forms. All right, so you'll be learning what other life forms this will be as we go on. So zombie feeding. When a zombie feeds, it affects the host with a virus. The virus then turns the host into a new zombie that joins your army. The new zombie's DNA will be calculated from the previous zombie's DNA and the host's DNA. Alright? And what do our zombies like to feed on most? Find out. You'll have to complete lesson 2. Okay? So this is how we'll be generating new zombies. Okay, when our zombie feeds on a host, the new zombie's DNA will be calculated from the previous zombie, that's the original zombie, right? And then the host zombie, right? So the combination of these two, that's the zombies that were fed on and the zombie that. So the combination of these two would produce the new zombie's DNA, right? Okay. So put it to the test. There's a simple demo to feed into the right. Click on a human to see what happens when your zombies feed. Okay. So this is a demo to the right. You can see that the new zombie's DNA is determined by your original zombie's DNA as well as the host DNA. So this is our zombie right here, and these are humans. Okay. Okay guys, welcome to chapter 2 of lesson 2. Okay, mappings and addresses. Let's make our game multiplayer by giving the zombies in our database an owner. Okay, so now we've been able to create the functionalities that help us in creating zombies, right? But how do we know who owns the zombies? Okay, we have zombies, but we don't know the owner, right? So we want to be able to create the functionality that will help us in setting owners for these zombies. Okay, to do this, we'll need two data types: mapping and address. Addresses. What are addresses? The Ethereum blockchain is made up of accounts, which you can think of like bank accounts. An account has a balance of Ether, and this is the Ethereum. This is the currency used in the Ethereum blockchain, right? And you can send and receive Ether payments to other accounts, just like your bank accounts can wire transfer money to other bank accounts. So this is my MetaMask wallet now. Okay, so let me show you what an account looks like. So these are my accounts, right? These are all Ethereum accounts. Okay. And anytime you interact with the Ethereum blockchain, you must use an account to interact with it. Okay. So if you are going to be sending Ethereum to someone, or sending a token to someone, or even purchasing an NFT online, or just whatever transaction you are performing on the Ethereum blockchain, you must use an Ethereum account to what? To perform these transactions. So these are all you know, accounts on the Ethereum blockchain. Okay. So and you must, and each account has an address, right? So you can see this 0x146 right here. This is the address of the, all right. So that is what it is. Each account has an address, yes, like I've shown you, which you can think of like a bank account number. It's a unique identifier that points to that account, and it looks like this. Okay, so this is how an Ethereum, a MetaMask address will look like, or still called an Ethereum address, right? So this is how it looks like. It's actually a long digits, alphanumeric digit, right? So this address belongs to the CryptoZombies team. If you're enjoying CryptoZombies, you can send us some ether. So this address actually belongs to what? CryptoZombies. So if you know you're enjoying this platform and it's of great help to you, show them some love, okay? So yeah, we'll get into the nitty-gritty of addresses in a later lesson. But for now, you only need to understand that an address is owned by a specific user. Okay? So we can use it as a unique ID for ownership for our zombies. When a user creates new zombies by interacting with our app, we'll set ownership. So basically, whoever called the create zombie function would take the account address, the Ethereum address, and set it as the owner of that zombie that was created. Okay, so that is that. So mappings. In lesson 1, we looked at structs and arrays. Mappings are another way of storing organized data in Solidity. So if you can remember, in lesson 1, we talked about structs and arrays, right? This is an example of a struct here, right? And this is an example of an array. An array will look something like this. Okay. One, and it can hold several values. Okay. So that's how an array would look like. And yeah, so there are something, and yeah, okay. So and if you look at these three data types, there are similarities between them. There is something that is similar among the three of them. So you will notice that these three data types allows us to what? Hold multiple data. So basically what this could mean is that we are mapping addresses to the balance that these addresses hold. So you could say these addresses holds certain account balance, maybe 0.2 ETH, or 1 ETH, and so on and so forth. So this is just a mapping of addresses to what? Account balances, right? Okay. And account balances in this case is going to be a numerical value. That is why we have it as a uint data type here. Okay, so this is another example of a mapping. And this mapping is, so a mapping essentially is essentially a key value store for storing and looking up data. In the first example, the key is an address, all right? So the key here is usually the first. So here, the key is an address. The value is a uint, right? In the second example, key is a uint. Key is a uint here, and the value is a what string. So basically, mappings are a way we can store and look up data in Solidity. It helps us to store this data in a key value pair format, right? So how does this work? Okay, for example, we could come to this mapping now, this account balance mapping, and say, okay, all right, get us the account balance of this particular address. So we just put in the address and then it will spit out the account balance of that particular address, right? So here also we can just say, okay, get me the name of the user with this particular ID. Get me the name of the user with this particular ID. Then we impute the ID, then it spits out the username, right? So that is how mapping helps. That is what mapping helps us with, storing and looking up data. Now let's put this to test. To store zombie ownership, we are going to use two mappings. One that keeps track of the address that owns the zombie, and another that keeps track of how many zombies an owner has. Okay. Another keeps tracks of how many zombie an owner has. Right. Number one, create a mapping called zombie to owner. The key will be a uint. Okay. We'll store and look up the zombie based on its ID. Right. The key will be a uint and the ID an address. Sorry, and the value and address. Okay. Let's make this mapping public. Okay. So let's start by creating this mapping. Right. Let me just copy this. How do we create a mapping again? We create a mapping by typing in the mapping keyword. Okay. And to remember how it's done, look at this right here. We use the mapping keyword and here, what do we have? We want to have a uint as the key and we to map to an address as the value. All right. So this is a mapping of what? Uint to address. And for you to know, address is a data type in what? Solidity. And it's a data type for Ethereum accounts, MetaMask addresses, right? So, and then we want to make this what? Public, right? We want to make this public and we want to call this zombie to owner mapping. All right. So this is the name of the. Welcome to chapter 3 of lesson 2. Message.sender. Now that we have our mappings to keep track of who owns a zombie. All right, so so we created these mappings here, and these mappings helps us to keep track of the owners of each zombie. So this mapping here is a mapping of what? Zombie to owner. So it keeps track of the zombies and their respective owners. And the owners here is, so basically what we'll be doing is to update this create zombie function to use these mappings that we created so that whenever a user creates a zombie, we can assign ownership of that zombie to the user, right? Immediately after the zombie has been created. So, and then we'll need something called message.sender to do that. Okay, so basically, message.sender is simply the address of the person or smart contract that is calling a function in an application at any given point in time, right? So, for example, if I was the one who called this create zombie function, the message.sender would be my MetaMask address that I used. So, one thing to note is that there will always be a message.sender because there must always be an external caller, right? In when dealing with Solidity, there must always be an external caller, right? Um, a smart contract deployed to the blockchain does nothing until it is being called by someone, right? So that is why a message the sender must always be present, because smart contracts are as good as nothing if no one calls them. They will just reside dormant on the blockchain. Here is an example of using message the sender and updating a mapping. Here we have a mapping called favorite number, and this looks like a mapping of addresses to numbers, and I think this number here is the favorite number. So addresses as people map to their favorite numbers. So we have two functions here. One is set my number and one is what is my number, right? So this set my number function retrieves and returns the value that this message.sender stored, right? So whoever called this function at first and stores my number, this function would return the value that the message.sender had stored in the set my number function. Okay, so if I was the one who called this function and then I store this number under my address in this mapping, all right, so this function will simply help me to retrieve and return the number that I stored. So it's a pretty much simple function. In this trivial example, anyone could call set my number and store a unit in our contract, right? So anyone could call this contract or this function, right? Because it's a public function, and then they can store my number or store a unit in our contract, which would be tied to their address, right? It will store the unit under their address, and then when they call what is my number, they will be returned the unit that they stored. So this function simply returns the unit that that person stores. Using message.sender gives you the security of the blockchain, of the Ethereum blockchain. The only way someone can modify someone else's data would be to steal the private key associated with their Ethereum address. So using message.sender is a safe way of dealing with accounts in Ethereum blockchain, because every account or every address has a private key, right? And let me show you what a private key looks like in Ethereum. If I go over to my MetaMask and I open it, okay, so this is my MetaMask, and each account that exists on your MetaMask, or each account that right now is where we'll be working with these two mappings we created. All right, so number one says, first, after we get back the new zombies ID, let's update our zombie to owner mapping. So what we want to do is to go under the ID of that zombie we just created and store message.sender, which is whoever called the function, under it. Okay, so how are we going to do that? So this is how we're going to do that. We're just going to say All right. We're just going to access the zombie to owner mapping, right? And then say, hey, get me this person, which is what message.sender. Get me this person who just called this function message.sender, right? And then what does this returns to us? It returns no, sorry, this would be actually not get me message.sender. This would be get me this zombie that was just created. By using the ID, would find the zombie, right? So get me this zombie that was just created. And remember, we are getting ID from here. Okay. So this will return us the zombie that was just created. And then we want to say, okay, we want to store this owner as the owner of this zombie. We want to store this person as the owner of this zombie. And the person would be message.sender because that is the person calling the function at this point in time. All right. Message.sender. Okay. So now what this simply does is that, all right, it goes to this mapping and says, all right, I want to store message.sender under this particular zombie. Okay. So that is that. And then number 2 says, let's increase owner zombie count for this message.sender. All right. So we know, so now we need to like increase the zombie count number stored in this mapping for this user, for this owner who just called or who just created a zombie, right? Because I mean, if he had 3 zombies before and then he just called this create zombie function, it sure means that he has a zombie of +1, right? So if you had 3. So welcome to chapter 4 of lesson 2, require. In lesson 1, we made it so you remember that in lesson 1 we created this function here that's called create random zombie. It's a public function and it takes in a name. Right? It takes in the name parameter. It uses that name parameter to generate a random DNA zombie, right? So, however, if users keep calling this function to create unlimited zombies in their army, the game wouldn't multiple times. All right, so let's make it so each player can only call this function once. That way, new players will call it when they first start the game in order to create the initial zombie in their army, sorry. How can we make it so this function can only be called once? And a conditional statement just tells a program to execute an action. That is the main purpose of conditional statements. All right, so down here you see a function, right, that uses the require statement. And what this function really does is it compares if name equals. So you can see right here, this require statement is performing a comparison between what? Name and vitalic, right? And this double equal to sign here is asking to mean, all right, so is name equal to what? Vitalic, are they the same? All right, so this equal to sign is just a comparison statement in Solidity that says, hey, check name and vitalic if they are the same, right? So Solidity does not have native string comparison. So we compare the K-SHARK 256 hashes to see if the strings are equal, right? So in Solidity, you cannot compare strings, directly, right? You can't compare strings directly. You need to wrap them with the K-SHARK 256 function, right? Whereas in other programming languages like JavaScript, you can do a direct comparison of strings So you can see does what? Does dog equal, plants? Sorry, plants. All right. So this is a direct comparison. Okay, so um, if you call this function with a vitalic argument, let's say a vitalic value, right? That this function above right here, if you call it with vitalic, it will return high, right? Why would it return high? Because the value of name here will be vitalic, and then vitalic will be equal to what? Vitalic here. So this will evaluate to true, and then the execution will continue to the next line, and high will be returned. But if you call this function with some other value as the parameter, this won't evaluate to true, right? It will definitely evaluate to false. And then what will happen? The execution of this code will break right here, and to throw an error and then stop execution, right? So it will come to this next line, and high will never be returned. Okay, so that's how conditional statement works. All right, in almost every programming language, right? So require helps us to write conditional statements in Solidity, right? So you're just telling Solidity, hey, I require this to happen before you move on to the next line of code. Thus, require is quite useful for creating certain conditions that must be true but running a function. Sorry, I didn't read that correctly. Thus, require is quite useful for verifying certain conditions that must be true before running a function, right? Put it to the test. In our zombie game, we don't want the user to be able to create unlimited zombies in their army by repeatedly calling create zombie. It will be fun. It would make the game not very fun, right? So right now, like I said, users have the ability to call this function as many times as possible, and thereby having unlimited amount of zombies, which is not really cool, right? So we want to place a restriction on that. All right, let's use require to. So in other words, if the person calling this zombie has no zombie in the wallet, this will return zombie for that individual. But if the person has then this will evaluate to false because it won't be equal to 0, right? So then what happens? The code execution stops here and it throws an error, right? And it doesn't go on to the next line of code, and doesn't, in essence, it doesn't create a zombie for that person. Okay. So let's see what you have to say here. It says, note, in Solidity, it doesn't matter which term you put first. Both orders are equivalent. All right. So what they're simply trying to say here is it doesn't matter if this comes first or the 0 comes first, right? It doesn't matter. So, but for this, okay, welcome to chapter 5 of lesson 2 called inheritance. Our game code is getting quite long. Rather than making one extremely long contract, sometimes it makes sense to split your code logic across multiple contracts to organize the code. One feature of Solidity that makes this possible, makes this more manageable, is called inheritance. So you can see that our contract code is getting quite long, right? So it makes sense for us to split this up. Baby Doge inherits from Doge. This means if you compile and deploy Baby Doge, it will have access to both cache fetch function that exists in Doge and another cache fetch function that exists actually in Baby Doge, right? So this means that because Baby Doge is inheriting This can be used for logical inheritance, such as with a subclass. A cat is an animal, but it can also be used simply for organizing your code by grouping similar logic together into different contracts, right? So what this is saying is inheritance can also be used in what logical classification, right? Where, for example, we have an animal here which can represent a parent contract. An animal here can represent a parent contract, while cats and other animals like dog, spider, and whatsoever can be classified as what subcontracts or children contracts, right? But in this case, we're actually using inheritance to just achieve organization of our code, right? So let's put this to test. So in the next chapters, we are going to be implementing the functionality of our zombies to feed and multiply. Let's put this logic to its own contract that inherits all the methods from Zombie Factory, right? So we want to create in a functionality that would help our zombies to feed and multiply, right? We're going to be putting this functionality in its own contract, right? Okay, welcome to chapter 6 of lesson 2 called import. Whoa, you will notice we just cleaned up the code to the right and you now have tabs at the top of your editor. Go ahead, click between the tabs to try it out. So you notice that we have two tabs here. One is called Zombie Feeding, the other one is called Zombie Factory, right? And so we've kind of like splitted our code across two files, right? So this is majorly very useful when dealing with large code bases, in real life scenarios, and when you're working on a project, you do not just want to have all your code written in one file, right? You want to spread them across different files to keep the code cleaner and more organized. Okay, so we're kind of like mocking that experience here by creating these two tabs. All right, they've already created these two tabs for us. Okay, so our code was getting pretty long, so we split it up into multiple files to make it more manageable. This is normally how you will handle long code bases in your Solidity projects, right? When you have multiple files and you want to import one file into another, Solidity uses the import keyword, right? So this is what the import keyword looks like, right? Just right this is the import keyword, and then followed by the file location, right? File location. So this is simply saying I want to import the file, the contract in this location into this file, to this present file, right? So which means in this contract we could have access to everything that lives in this file, right? So that's what the import statement allows us to achieve, right? You could have your code split across multiple files, but you would still be able to access, other files from another file, right? With the import statement. Okay, so if we had a file named this smart contract or so in the same directory as this contract, that's what the dot slash means. Okay, in case you did not know, the dot slash is simply a. All right, welcome to chapter 7, storage versus memory data location. Solidity, there are two locations you can store variables, either in storage or in memory. Storage refers to variables stored permanently on the blockchain. So there are two data locations that all your variables in Solidity are categorized under, right? First one is storage and the other one is memory. And what are the differences between these two? So you can think of them like hard disk versus RAM. The storage in this case is similar to hard disk in your computer because it is a permanent storage. It is anything stored in storage is stored permanently, right? While the memory data location can be similar to RAM because it is a temporary storage location, right? So that is the difference. Okay, so what this is simply saying is most of the times when writing Solidity code, we do not really need to specify, whether it's a storage variable or a memory variable, right? Because Solidity handles all these by default, right? So let me give you an example. Let's go back to our zombie factory contract. So you can see these variables we created here, like this, or like this one, or all these ones. They are all by default storage variables because they are declared outside a function. So Solidity treats them as a storage variable, state variables, you can call them also, right? Because they are stored permanently on the blockchain. But variables declared within a function, for example, this one, they are by default memory variables because it will disappear once the function call ends, right? So we do not really need to specify when creating these variables that okay, this is a storage or this is a memory. Solidity just knows how to handle them by default, right? So take note of that. However, there are times when you do need to use this keyword, namely when dealing with structs and arrays within a function. So it tells us here that there are specific times. So here we have a mySandwich variable whose value is set to the element stored in the index location in the sandwiches array, right? Sandwiches array we have over here. So let me go over this again. This is a declaration or a variable called what mySandwich, whose value is set to the element stored in the index location in the sandwiches array, right? So this line of code looks pretty straightforward and correct to the eyes, right? But in reality, the Solidity compiler will complain when you write it this way because it expects that you should explicitly declare the data location for it, either be it storage or the memory, right? Now, why is Solidity requesting that we should explicitly declare if it's a storage or a memory variable? Because, like we said, when working with structs and arrays within a function, it is required, right? Okay, so let me quickly explain what this pointer and permanent change is all about. So supposing we have mySandwich like this, right? mySandwich which we have here. If we have it like this set to an element in this array, okay, you see that mySandwich was set to an element in this array, right? And you know that whatever is in this array, right, this sandwiches array is of type what? Sandwich, which means it's going to have a structure of this format, right? It's going to have a name, which is of type string, and it's also going to have a status of type string. So it's going to come in this what? In this format, right? So let's say, for example, we have this set to something that looks like this. Okay, this is my sandwich set to a sandwich created by the sandwich struct, whose values is as follows. Name here in this case is Daniel. Status is equal to what? High value, right? So the name here is Daniel, and then the status is what? High value. So let's say we have this set to this for example, right? So this means if I should make a change, right, to the status property, like so, let's make this change to the status property by doing my what? Sandwich. My sandwich dot what? The status. Let's make it equal to what? Low status, right? So this means that this has been changed to low status, right? So which means declaring it like this has created a copy of this, a copy of another sandwich. So any modification we are doing right here, it's not updating the original value of another sandwich, but actually just updating the copy of it, right? So this still retains its initial value, but it's just the copy that is being updated here. Okay, sorry, we're supposed to name this another sandwich. All right. Okay, so this is actually a copy of this. So this is not actually this in real sense, but just a copy. So we are actually updating the copy here and not the initial property and not the initial variable. Okay. And why is that? Because we're using the memory keyword here. So this is how Solidity understands it whenever you use the memory keyword as compared to when you use the storage keyword. Okay. So I'm going to take this away and also take this away right here. Let's continue with the code, right? So that is the difference, right? One creates a copy of the variable. The other actually does not, but it makes the change directly on the initial variable. So that's the difference between the storage and the memory. But don't worry if you don't fully understand when to use which one yet. Throughout this tutorial, we'll tell you when to use storage and when you use memory. And the Solidity compiler will also give you warnings to let you know when you should be using one of these keywords. For now, it's enough to understand that there are cases where you will need to explicitly declare storage or memory. Let's put this to test. It's time we give our zombies the ability to feed and multiply. Okay? When a zombie feeds on another life form, its DNA will combine with the other life form's DNA to create a new zombie. Okay? So, first, let's create a function called feed and multiply to take two parameters, zombie ID, which is a uint, and the target DNA, which is also a uint. This function should be public. Okay? So, let's start right here. Create a function called what? Feed and multiply. So let's just copy this, paste it right here. It says this function takes in two parameters. Two parameters. One, it's a uint called what? Zombie ID. And then the other is a uint called what? Target DNA. Okay, and then it's a public function, right? A public function. Okay. So number 2 says we don't want to let someone else feed our zombie. So first let's make sure we own this zombie, right? Add a require statement to verify that message.sender is equal to the zombie's owner, similar to how we did in what create random zombie function. So if you remember the create random zombie function, we did something like this, right? So we want to also do something like this, right? So I'm just going to copy this, right, and just modify it right here. Okay. So right, so we want to add a require statement to verify the message.sender, right? So I'm just going to delete this right here. Your message.sender is equal to what? The zombie's owner. It's equal to the zombie's owner, which will mean you know, the feed and multiply function. The formula for calculating a new zombie's DNA is simple. It's the average between the feeding DNA, the feeding zombie's DNA and the target's DNA, right? So remember that our zombies now have the ability to feed on other life forms, right? The target here in this case is other life forms. So these other life forms could be, a human or a new zombie, right? So when this happens, a new zombie is created, right? And the DNA for this new zombie is going to be derived by finding the average between the feeding DNA or the feeding zombie's DNA and the target's DNA, right? The target here is the zombie or the human that has been fed upon, right? So you can see that, for example, here we have a function called DNA test DNA splicing. Here we have a DNA, and this is its. Here we have a zombie, and this is its DNA, right? And here we have the DNA of a target, right? So you can see that a new zombie's DNA is generated. This new zombie's DNA was just gotten by finding the average between the zombie that fed on a life form and then the target that was fed upon, right? So the average between these two generates the new zombie's DNA, right? So this is the formula we're going to be using to generate the zombie of the DNA that was formed after our zombie fed on a life form. Hope that is clear, right? So later we can make our formula more complicated if we want, like adding some randomness to the new zombie's DNA. But for now, we'll keep it simple. We can always come back to it later, right? So let's put this to test. First, we need to make sure that target's DNA isn't longer than 16 digits. Now you remember that our DNA must always maintain a length of 16 digits, right? That is nothing more, nothing less. It must always maintain a length of 16 digits. Now to do this, to ensure that the target's DNA is always 16 digits, we need to what? We need to set target's DNA equal to the modulus of these two, right? Target DNA modulus against DNA modulus to only take the last 16 digits. Now, if you remember in our previous contract, we did something similar to this. You can see that after we generated a random integer number here and we stored it in rand, what did we do? We found the modulus of rand and DNA modulus. And this was to make sure that it's of 16 digits, right? The value of DNA modulus here is 10 raised to the power of 16, which 16 here is DNA digits, right? So this was also to make sure that it's of length 16 digits. Okay, so that is the same thing we want to do here. The target DNA that is coming from as a parameter in this function, we want to ensure that, okay, that is of length 16 digits. And how do we do that? We just say target DNA should be equal to what? Target DNA modulus 1, DNA digits, DNA modulus, okay? So remember that, okay, this should be U here. And remember that the only reason why we have access to DNA modulus in this contract is because we've imported the zombie factory, right? Okay. So note, you can access the, number 2. Next, our function should declare a So welcome to chapter 4 of lesson 2, require. So even though we imported it, we do not have access to it here because it has been marked as private. So which means other contracts that imports zombie. So that is what the private keyword does, right? To a function or even a variable that's been marked with it. All right. So what we need to do now is to modify this function with another visibility, which we're going to speak about in a second, right? We're going to change this to another visibility that gives it access to our zombie feeding contract here. So let's look at internal and external. In addition to public and private, Solidity has 2 more types of visibility functions called internal and external, right? So apart from public and private that we've been working with all along, there exist 2 more types of visibilities in Solidity, which is what? Internal and external. Now, internal is the same as private, except that it is also accessible to. So this function marked as private is only accessible within this contract, within the zombie factory contract. Any other contract importing the zombie factory contract wouldn't have access to it. But with internal, that is not the case. Other contracts importing this contract would have access to it. So that is the difference between private and internal. So this looks like what we would need to do here. We'll need to change this as internal. We'll change this to internal. Okay. So external is similar to private, except that these functions can only be called outside the contract, right? They can't be called by other functions inside that contract. We'll talk about why you want to use external versus public later. All right, so the difference between external and public is that external functions cannot even be called within your contract. They can only be called by entities outside your contract, outside your project. So that could be a person calling your function, or another contract calling your function, right? But external functions cannot be called within your code base, all right? Whereas public functions can be called both within your code base and from external entities outside your contract. All right, so we'll be looking more at this as we move on. For declaring internal or external functions, the syntax is the same as private and public. Okay, so here we have an example. This is a contract called sandwich. It has a private variable, right, called sandwiches eaten set to 0. And then there is a function that exists within this contract called it, and it's an internal function. What this function does is that it increments this variable right here. All right. So this is a contract called BLT. This contract. Hello? 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 All right. Welcome to chapter 10. What do zombies eat? It's time to feed our contract. And what do zombies like to eat the most? Well, it just so happens that CryptoZombies like to eat crypto kitties. Yes, I'm serious. With a laughing emoji. Haha. Alright, so in order to do this, we'll need to read the kitty DNA from the crypto kitties smart contract. We can do that because the crypto kitties data is stored openly on the blockchain. Isn't the blockchain cool? Don't worry, our game isn't actually going to hurt anyone's CryptoKitty. We are only reading the CryptoKitty's data. We are not able to actually delete it. Alright, so we want to have our contract interact with another external contract that has been created by someone else and has been deployed to the blockchain. So we want to have our zombies feed on kitties. So we need to interact with the CryptoKitties smart contract in order to extract or read the DNA of these kitties from the contract, right? So how do we interact with another contract? How do we have a contract interact with another contract? All right, so that leads us to interacting with other contracts. For our contract to talk to another contract on the blockchain that we don't own, remember that we do not own this CryptoKitties contract, right? But we need it for some reasons. We need it because our CryptoZombies love to eat CryptoKitties, right? And we need the DNA of these CryptoKitties, of these kitties, right? So, but we don't own these CryptoKitties. We were not the one who created it. It has been deployed on the blockchain by someone else. So, first, we will need the interface of the CryptoKitties contract if we want to interact with it, right? And this also goes to apply to any other contract out there. If you want to interact with an external contract, the first thing you will need is an interface of that contract you want to interact with. All right, let's look at a simple example. Say there is a contract on the blockchain that looks like this. All right, so let's assume that this is a contract on the blockchain that looks like this. And this is a contract called lucky number. And then it has a mapping called numbers. And this is a mapping of addresses to uints, right? And then it also has a function called set number, and it takes a parameter called num of type uint, and it's a public function, right? Public function. So this function only does one thing, right? This set my number function only does one thing. It says here, hey, look me up this particular address in this mapping, right? Look me up this particular address in this mapping and then store this lucky number under it. All right. Okay, so let me go over that again. It says, hey, look me up this particular address inside this mapping. And then when it is found, store this number, this lucky number under it. Okay, so this is like a key to value pairing. All right, so address is the key and then the lucky number as the value, right? So here we have another function called get number, right? It takes in an address as the parameter, right? It's a public function. It's a view function because it just returns a value. it does not modify or change a value like we have here, right? So this is just a view function because it returns a value, right? And then this function returns a uint value. All right, so what is this function doing right here? It's simply just saying, all right, return me the number that was stored under this address, right? Return me the lucky number that was stored under this address. Okay, so that's simply what it's doing. So it goes into the mapping, and then, all right, return me the number or the lucky number that was stored or that is associated with this address. Okay, this would be a simple contract where anyone could store their lucky number and it will be associated with their Ethereum address, right? So anyone could call this function and store their lucky number under their Ethereum address, right? Then anyone else could also look up that person's lucky number using their address. So for example, I could come to this contract and call this function and then pass in anyone's address, and then it will bring out or it will spit out the lucky number of that person, right? So now let's say we have an external contract that wants to read the data in this contract using the get number function, right? Let's say we have, this is a contract, right, that has been deployed and to the blockchain. So let's say we want to interact with this contract to get the lucky number of anyone, right? We want to do that by what? By interacting with the get number function. Okay. So we want to have our function. So we want to have our contract read the data in this contract, right, using the get number function. Okay, the first thing we will need is the interface of this contract, the lucky number contract. And how does an interface of a contract looks like? And this is an example of an interface. This is an interface of this contract, of the lucky number contract, right? So this is an example of an interface, how an interface looks like. Okay, you would see the differences between an interface and a all right, notice that this looks like defining a contract. Okay, so this is what an interface of a contract looks like. Now you notice that this looks like defining a contract, but with a few differences. For one, we are only declaring the function we want to interact with. In this case, the get number function. And we don't mention any of the other functions or state variables. So you can see that we are only declaring the get number function, right? And we are not even writing the body of the function. We don't need to declare the body of the function, just the declaration, right? And then we don't need to write the other variables or state variables within the contract, right? So it's just like a bare bones structure of the contract. Okay. Secondly, you will notice, we are not defining the function body. Yeah, like I said, you can see that we are not defining the function body. So instead of the curly braces, we are simply ending the function declaration with a semicolon. You can see right here, we just simply ended it with a semicolon, right? So it's kind of it kind of looks like a contract skeleton. This is how the compiler knows it's an interface. Okay, so it's just like a skeletal structure of the whole contract, right? So that's just how that's just the difference between an interface and the contract itself, right? So you can think of like an interface like the table of contents of a book, right? So the table of content just tells you what the book contains, but it doesn't contain the details of each pages of each chapter, right? It just gives you a skeletal structure of the book, right? So that's how an interface is. By including this interface in our dApps code, our contract knows what the other contracts function looks like, how to call them, and what sort of response to expect. So you can see that this contract, by importing it in our code, if we want to interact with this contract, for example, by importing the interface in our code, it already tells our code that, all right, so this contract has a get number function, right? It gives us this very important information. It has a get number function, and this function returns what? A value. So we are going to be expecting a uint value, right? And this function needs a parameter to be called, right? It needs a parameter while calling it, and the parameter is an address of type address, right? So interface simply just gives the information about that contract to your code, right? So how to call it, what parameters to pass in, what sort of response to expect, and how the function structure looks like, and things like that. But we'll get into actually calling the other contracts function in the next lesson. But for now, let's declare our interface for the CryptoKitties contract. Let's put this to test. We've looked up the CryptoKitties source code for you and found a function called getKitty that returns all the kitty's data, including its genes, which is what our zombie game needs to form a new zombie. The function looks like this, all right? So this is the source code from the CryptoKitties contract, and then this is the getKitty function, all right? So this function returns all what we'll be needing, right, for a new zombie, to generate a new zombie after feeding on the CryptoKitties, right? So so you can take a look at this. You can see that this is a getKitty function. It takes in an ID. It's an external function, right? So it's external because that is the reason it's external, and that's the reason why we can interact with it, right? If it had been private, we wouldn't be able to interact with it. And also, if it had been internal, we wouldn't be able to interact with it. All right. So it returns a bunch of values. Okay. This function returns a bunch of values. It returns a boolean of a boolean called is gestating, boolean called is ready, a uint called cooldown. So all these values are being returned in this function, and this is the body of the function here. You can see, right? You can see and this is the body of the function here, and you can see that each of these values are being set here, right? The is gestating variable is being set here, so and so on and so forth. This function looks a bit different than we are used to. You can see it returns a bunch of different values, right? Like I said, it returns a bunch of different values, right? Okay, so if you are coming from a programming language like JavaScript, this is different. In Solidity, you can return more than one values from a function, right? So take note of that. Now that we know what this function looks like, we can use it to create an interface. Okay, now number one, define an interface called Kitty interface. Remember, this looks just like creating a new contract. We use the contract keyword, all right? So let's create an interface here, and you just create an interface the same way you create a contract. You use the contract keyword, and then what? The name of the interface. Okay, in this case, it's the Kitty interface, and then followed by our curly brackets. Then number two, inside the interface, define the function getKitty, which should be a copy and paste of the function above, but with a semicolon after the return statement, instead of copying everything inside the curly braces. All right, so we just want to define the getKitty function, right? Remember, it's an interface we're writing, so because an interface, we just need to what? Copy only the declaration. We don't need to copy the body, and then paste this right here, and then end it with a semicolon, right? So it's just a declaration. So this just tells our contract, this just tells our zombie feeding contract that, hey, this contract, this CryptoKitties contract has a function called getKitty, and this function is external and it returns a bunch of values, right? And also, in order to call this function, we need a parameter passed into it called ID, right? So yeah, an interface is basically just giving information to your code on how to interact with that external contract, right? So let's click check answer and see if we're correct. All right, voila, we're correct. Next chapter. Okay, welcome to chapter 11, using an interface, right? Continuing our previous example with number interface, once we have defined the interface as this, we can use it in a contract as follows. Okay, so remember from the previous chapter, chapter 10, we were talking about a lucky number contract, right? And we defined an interface for that contract, and this was it, right? So how do we use this interface in a contract? Okay, so this is the address of the number interface, right? The number interface address. So once we've gotten the address, how do we get the contract? Now you can see that they are declaring a variable here called number contract, and it's of type what? Number interface. Now, how do we get a contract? Now, remember, now take note of this. A contract is usually the combination of the interface and the address. Okay, so you can see here that we're combining the number interface with its address to get the number contract. Okay, let me go over this again. A contract is usually the combination of its interface and its address. So you can see here that we are combining the number interface, right, with its address, and this would give us the contract. Okay, so whenever you want to interact with a contract, whenever you want to interact with an external contract, you first need its interface, right? You first need the interface, and then you need the address. Okay, so in order to interact with the contract, in order to generate the contract in your code base, you need to put the combination of the interface that you have gotten and the address. So the combination of the two of them would give you the contract. And then you can begin to work with this contract to interact with the data and the resources on it, right? Now see on the next function how we interacted with this contract now. All right, in this function, you can see that we are calling the get number function on it, right? We have the contract. Now we can call every function on this contract. All right. If you remember in chapter 10, I think I should go back a bit. Let's go back a bit to chapter 10 and remind you of what is going on there. Okay, so you can see, right? This is the get number function we are calling, right? This is the get number function we're calling. This was the interface we got, right? And with this interface and the address, we were able to get access to the contract, all right? And this is the contract we're working with here. This is the contract we're working with here now. And on this contract, we are calling the get number function. Do you see how it works now? We are able to get access to this contract by combining the number interface and its address, right? So after getting the contract, we can be able to call every function that exists on this contract. So even we can call the set number function, right? Although in this case, we don't need it, but I'm just saying that you can call the set number function. You can access any variable, that is opened externally to be called, right? So now we are calling the get number function and passing in this address. And then what happens? It retrieves so it retrieves the number that is stored on the all right, welcome to chapter 12 called handling multiple return values. This getKitty function is the first example we have seen that returns multiple values. Let's look at how to handle them. So remember our getKitty function, right? And remember how it returns a bunch of values, right? You can see that it returns a bool value, which is called isReady, cooldown index, next action at, and so on and so forth, right? So you can actually have a function return a ton of values. But how do you handle them, right? When we call this function and it gives us a ton of values, it returns to us a ton of values. How do we handle those ton of values that were being returned to us? Okay, so let's look at this example here. We have a function here. We have a function here called multiple returns. You can see it's an internal function and it returns 3 values. The first one, A, which is a uint. The second one, B, which is a uint. And the third one, C, which is a uint. And you can see in the body of the function, it just returns 3 values in one line. 1, 2, 3, right? The next, we have a function called process multiple returns, an external function. And you can see that 3 variables are being declared here, A, B, and C, all of which are uints. All right. And what do we have here? What we have here is called multiple assignment. Now you can see that A, B, and C are being assigned the values that returns after multiple returns is being called here. And remember that what returns after multiple and remember that the multiple returns function returns 3 values called 1, 2, 3, right? So which means A, B, and C are being assigned these values respectively. One is assigned to A, 2 is assigned to B, and 3 is assigned to C. All right. So that is what multiple assignments looks like. Or if we only cared about one of the values, all right. So this is a function now that just cares about one of the values, all right. We don't want the first value, we don't want the second value, we just care about the third value, right? So right here, this is how it works. You can see that we have 2 commas and then the last one, which is C. So what this will do is that Solidity would return this statement, return this function, but only the last value will be saved to C. It will ignore the first 2 values, right? Because this just tells this Solidity that, all right, yes, I know there is 2 values here, but ignore them, right? So that is how it works, okay? Now, or if we only cared about one of the values. Okay, so there are some times when you don't want to do everything. So there are some times when you only care about one of these values being returned from a statement, from a function that you called, right? So for example, let's say we don't want the first value and we don't want the second value. We just want 3, the last value, right? So you can do something like this. You can see here that there are 2 commas before the last C, right? So this just tells Solidity that, hey, we don't want the first value, ignore the second value, just give us the third value. So what happens here after you call multiple returns is that, all right, it ignores 1, ignores 2, and then it assigns 3 to C. Okay, so this is how you do it when you don't necessarily want to use all the values. Okay, you just put in a bunch of commas without no space. All right, you put in the commas without space, and Solidity would know that, okay, let's ignore these values and treat the values that were specified. Okay, number 2, the function should then call the kitty contract.getKitty function with kitty ID and store genes in kitty DNA. Remember, getKitty returns a ton of variables, 10 to be exact. I am nice, I counted them for you. But all we care about is the last one, genes. Count your commas carefully. Alright, so we want to call the getKitty function that exists on this contract, right? And remember that it returns a ton of value, but we are only concerned about one value, which is the genes, right? We are going to ignore the rest. And remember how to ignore values that you don't need by using the commas, right? So we will ignore these first 9 values, and then this 10th value, the last one, is what we need. Okay, so let's go ahead and do what we were asked. So let's call this function, all right, the getKitty function. Okay, and then pass in the ID. Remember, it takes in a parameter of ID, right? The kitty ID. So we're just going to pass in the ID here and tell it, get this kitty for us. Get the kitty with this ID for us, right? Okay, remember the kitty contract is the kitty contract we have generated above here by the combination of the interface and the address, right? So with this, what happens is that it returns us a ton of values, okay? A ton of values, but we are only concerned with the last one, the genes, which is also the same thing as the DNA. So we want to store the DNA, or in this case called the genes. We want to store it in this variable we created above, right? So we're just going to say kitty DNA, right? Okay, Now remember that this function is not only now remember that a ton of values is being returned here. Okay, so what do? We just wrap this with a bracket and then use commas to ignore the first 9 values: 1, 2, 3, 4, 5, 6, 7, 8, and 9. All right, so we're just telling Solidity, hey, ignore this first 9 values. Chapter 13, CryptoZombies. Our function logic is now complete. Let's add in one bonus feature. Let's make it so zombies made from kitties have some unique feature that shows they are cat zombies. To do this, we can add some special kitty code in the zombies DNA. If you recall from lesson 1, we are currently only using the first 12 digits of our 16-digit DNA to determine the zombie's appearance. So let's use the last 2 unused digits to handle special characteristics. So we want to add a special feature for our zombies that are made from cats. Zombies that were formed from feeding on kitties. So this special feature would be unique to those zombies, and it will distinguish them from other regular zombies. Okay, so remember that our DNA is of 16 digits, but currently we are using only the first 12 digits, which means the last 4 digits are not in use, right? We're using the first 12 digits to determine our zombie's appearance, but the last 4 digits are not serving any purpose. But now, since we want to introduce a special feature for our zombies that come from cats, we would use the last 2 digits of the 16-digit DNA to be responsible for that special feature. Okay, and how are we going to do that? We're just going to do that by saying, hey, if this zombie comes from a cat, give the last if this zombie comes from a cat, make the last 2 digits of its DNA to be what? 99. All right, so we're going to be using an if function to do that. Okay, so that brings us to the if statement. If statements in Solidity looks just like JavaScript. Okay, so here's a function called eatBlt, takes in a string called sandwich, and you can see that here is the if statement, and the if statement is doing a comparison. Okay, and remember, with strings we have to compare their K-shark hashes to check equality, right? So we cannot compare strings. Okay, number 3. Inside the if statement, we want to replace the last 2 digits of DNA with 99. One way to do this is using the logic this, right? So what does this logic mean? All right, I'm going to take my time to explain this shortly. All right, but let's just see the explanation they gave right here. So assume new DNA is 334455, then new DNA modulus 100 will be 55. That is, this new DNA modulus 100 will be 55. Then new DNA minus new DNA modulus 100 will then be what? 334400. Finally add 99 to get this. All right, so basically let me just explain it in my own language. All right, so I'm going to copy this and paste it right here. Okay, just watch me as I explain. So what is 334455 modulus 100? Remember, the modulus is always the remainder after a division, right? All right, so let me pull out my calculator and solve this. Right? So 334455 divided by what? 100, divided by 100, and then all right, so the remainder is what? 55. Okay, the remainder is 55. The value after the decimal point is the remainder. All right, so 55 we would have here. Okay, so 55 we would have here. Right, the next, let's solve this. Okay, let's solve this. Let's evaluate this. 334455 minus 55 would be what? Would be what? Would be this. Okay, new DNA 334455 would give 3344 then 00, because when you take away 55 from this, we'll be left with 00 at the end here. You can try that in your calculator and see what it gives you. All right, so then the next thing would have at the end is 99, and then when you add 99 to this, what would we get? We'll get to be equal to 33445599. All right, so that is how, sorry, no longer 55. The 00 will be replaced by 99. We can try it out and see if you are confused. All right, so 334400 plus 99 is what? You can see, right? So that's that. So that is how they arrive to this. Okay, 99. Finally add 99 to get this. All right, so that's the evaluation of this logic, of this logical expression here. All right, so this is how we are going to be adding 99 to the DNA of zombies that comes from cats. All right, so that'll be that. So let's add this within our function, within our if function. Okay, let me delete all of this. Okay. All right, welcome to chapter 14, wrapping it up. That's it. You have completed lesson 2. You can check out the demo to the right to see it in action. Go ahead. I know you can't wait until the bottom of this page. Click a kitty to attack and see the new kitty zombie you get. All right, so let's try it out. This is our zombie, and then we are going to feed on a kitty. So these are 3 kitties here. So which one should we feed on? All right, so I'm going to feed on this one that looks a bit unique and see what it gives us. So I'll just click on it, and then voila. So you can see this is our zombie, our cat zombie, our zombie generated from a cat, from feeding on a kitty, right? So let's try another one. We'll try another one and see how this one looks differently. Okay, all right, see how this one looks. So this is the beautiful thing we've created so far. All right, so here we have JavaScript implementation. Once we're ready to deploy it to the contract to Ethereum, we just compile and deploy zombie feeding, since this contract is our final contract that inherits from Zombie Factory and has access to all public methods in both contracts. So what this is saying is that once we are ready to deploy, right, so compile and deploy, we are just going to compile and deploy this. Let's look at an example of interaction with our deployed contract using JavaScript and Web3.js. So this is just an example. This code would show how the front end would interact with our deployed contracts, right? Because we are building an application and users are going to interact with the front end, right? They're going to interact through an interface. All right, so this is how the implementation would be written on the front end, right, to interact with our contract. So let's go through this code. All right, so here we have an ABI. ABI will be generated by the compiler. So the ABI is similar to the interface thing we spoke about in our previous lessons. All right, so ABI, the full meaning of ABI is application binary interface. All right, so here, this is how to get the ABI. Don't worry so much about this. All right, this is not the scope of this tutorial, but here we are getting the ABI, right? And then this is a variable called contract address, right? So remember how I told you that the combination of the ABI and the contract address would give you the contract itself, right? So that's what is being done here, right? So this is the zombie contract, the zombie feeding contract. We pass in the address, and then it gives us the zombie feeding contracts that we can work with, right? We call our contracts. When the user clicks, we call our contracts feed on kitty method, right? Our feed on kitty method that we wrote in the last chapter, right? So on this contract exists the feed on kitty function, and then we pass in the zombie ID, our zombie ID, then the kitty ID we want to attack, right? And so we're listing for a new zombie event from our contract so we can display it. All right, so when this event has been fired on the front end, we are going to listen for it. Okay, so when the new zombie event has been listened to on the front end, then if there's any error, so if there's any error, it will return and then break execution. But if there's no error, the function will display the zombie like in lesson 1. All right, and so it generates a zombie with the DNA, the name, and the zombie ID, and that's how this zombie is being generated right here. Okay, so this is just the front end implementation. You don't need to bother too much about this, but just to show you how things is going to be controlled on the front end, right? The user interaction process. So what the user is going to be doing, clicking some buttons here and there, and the zombie will be generated. So give it a try. Select the kitty you want to feed on. The zombie's DNA and the kitty DNA will combine, and you will get a new zombie in your army, right? So before you tried it out already, so you can still try it out if